In the last video, or in the previous video, I showed you a lower bound, right? I showed you a reduction from convex hull sorting, which means that we showed that if we could compute the convex hull of these blue points, then we can sort the numbers. And therefore, we try to conclude that therefore convex hull will have an n log n lower bound. That statement is a little bit imprecise, because how do we know sorting requires n log n time? The only argument that I know, or the one that you probably know as well, is that the lower bound of omega n log n for sorting applies only to the comparison model. So this lower bound is only comparison based. What this means that if the only operation you're allowed to do are comparisons, okay? But of course, when it comes to convex hulls and points, we are allowed to do other operations, right? For example, you could manipulate the points. You do sidedness tests. For example, given 2 points, you can draw a line through them and check whether another point is above or below. That operation obviously is much more complicated than just comparing 2 x coordinates. So therefore, it might be possible to compute the convex hull of these points, or in other words, to sort these numbers using these more complicated operations, such as sidedness tests. It sounds unlikely that you can sort a bunch of numbers in 1D by turning them into 2-dimensional points and then using 2-dimensional operations on them to sort them, right? Because that seems like kind of silly and improbable. But strictly speaking and mathematically speaking, that's a gap in our lower bound. That this lower bound only applies, lower bound for sorting only applies for comparison-based algorithms, whereas on this side, we have more complicated operations. One way to fix it is to define an algebraic decision tree model. I'm not going to define this model. I'm just going to show you a much weaker result that we can get with what we have already. But briefly speaking, in the algebraic decision tree model, you try to extend the notion of comparisons. So comparison, for example, when it comes to 2 points, if you compare the x coordinates of 2 points, you can decide whether a point to the left or to the right of another point. Then comparison can be represented algebraically by computing the sign of this expression, right? If you decide the sign of this expression, then you know whether x1 is smaller than x2 or larger than x2, or they are equal. And in general, this can be thought of as a polynomial. So in the algebraic decision tree model, you could try to evaluate the sign of more complicated polynomials than this. And then you can show that even with those more complicated polynomials, you can do better than n log n when it comes to sorting. But as I promised, I'm not going to do that. I'm going to do something simpler. So let's say I'm looking at algorithms, convex hull algorithms, that only use sidedness tests. Okay? So the only operation that we're allowed to do for these algorithms is that given points AI, so the algorithm, like, let's put it this way, the algorithm can pick 3 points. So I can pick, say, PI, PJ, and PK, and ask whether the line through PI, PJ goes above or below point PK. In other words, the line through PI, PJ goes above or below point PK. So above or below PK, right? So let's say that's the only operation you can do. If that's the only operation we can do, then we can actually show the lower bound, right? Because when you pick a point PI, so let's say this is point I, and this is point J. In this reduction, which points pass below the point PI and PJ? Only points whose x coordinate lie between point I and J. All the other points are above this line. Okay? In other words, PK is below the line through PIPJ if and only if its x coordinate lies in between. So if and only if xk is between xi and xj. So in other words, one-sidedness test can be replaced or simulated by just two comparisons. In other words, the sidedness tests that we're using here are only a constant factor more complicated than comparisons. Actually a factor 2, because you could maybe simulate two comparisons with one-sidedness test, but you can't do much more than that. So therefore, if you could sort a bunch of numbers using, say, m sidedness test, then you can also sort them with 2 times m comparisons. Since we know that if you sort a bunch of numbers with a bunch of comparisons, then this value should be at least omega n log n, then it follows that m should be omega n log n. Okay? But this only applies to algorithms that use only sidedness tests by picking 3 points and asking sidedness test queries on them. It does not apply to much more complicated algorithms than that. And if you want to strengthen this lower bound, then you have to look at slightly more complicated or more complicated models such as algebraic decision tree model.